Welcome back to the Foundations of the Computational Economics course. This time we're talking about linear programming and optimal transport models. Linear programming, this is a quite old field in economics, developed in the middle of 20th century. It has to do with finding maximum or minimum of a linear objective function subject to a set of linear inequality constraints. Very, classical problem in operations research in economics. It was originally developed to find optimal allocation plans for resources in, in economy, such as planned economy. Now, the optimal transport problem is probably one of the most actively developed to this day subfields in linear programming. And here the problem generally is to transport a set of goods from M origins to N destinations, minimizing the cost, where the cost of transportation is given by a matrix, each element of which, Cij, gives the cost of transporting from origin I to the destination J. Now, these optimal transport models actually find applications in many different fields. For example, in matching and trade, you can think of matching different distributions, for example, distribution of workers to distribution of firms. It is related to the gravity equations in trade models. With demand estimation and pricing, there is a relationship between the linear programming models and discrete choice and nested discrete choice. The quasi-linear hedonic models can be represented as optimal transport models. And sort of more generally, quantile methods in econometrics. More generally, this theory, which is well developed and well optimized, can be applied in several different fields. Now, let's look at this sort of generic representation of a transport model. You have a matrix of the costs in the Ci or C11, C12. These are the costs of transporting goods from from each of the suppliers down to each of the demands. So from A's to B's. And of course, the objective is to minimize this transportation cost. So we are minimizing this this linear function, which sums up the cost of transporting each of the Xij's goods from the origin I to the destination J. And we have to make sure that the following budgets hold. All the goods that leave destination I have to exhaust essentially the amounts of goods in that destination, and the goods that arrive at destination J, they have to sum up to the demand at that destination. And obviously, all Xij's have to be non-negative. All right, so going from the transport problem to the general linear programming problem, we can write that, in the most general case, the linear programming is basically maximizing, could be minimizing, a linear function which is given by the product of two vectors, C and X. X can have many variables, subject to the matrix A times X less than or equal B. Now, of course, AX less than or equal B also includes the conditions for the axis to be non-negative. Obviously, by setting the row of A to all zeros except for 1, and minus 1 rather, and the corresponding element of B to 0, we can include the non-negativity constraints into the AX less than or equal to B. And then similarly, we can impose equality constraints by setting two inequality constraints in the opposite direction. So So how can we represent the problem graphically? Well, think of the rows of matrix A multiplied with the column vector x of variables being less than or equal to an element in vector B, also a column vector. That gives us a line, right? So for example, A3 times x equals B is this line, and if we want to be on one side less than or equal to B, then we could be on one side of this line. So everything which is sort of to this side of the line would satisfy this one constraint. Everything that to this side of this other line, A2x less or equal B2, will be on the side which would be allowed, would be admissible. And, you know, considering all of the rows of matrix A, we can see that the set of admissible x's is forming a convex polygon, okay, in 2D. And we have to find an x inside of this set, which maximizes the objective function. Here's another picture. We also have a 2D case with two variables. A polygon is drawn in blue, and the red lines, these are the level curves of the objective function. Well, because the objective function is linear, then these level curves are actually lines, and you can see how one of the vertex gives the minimum solution and one other vertex gives the maximum solution of the linear programming problem. So you could think of this as being sort of a combinatorial problem of finding the vertices and then trying to find a vertex which maximizes or minimizes the value function, or the objective function, rather. Okay, of course there can be a case where the curve, the red line, right, the level curve, is exactly parallel to one of the faces of the admissible set, and then you have multiple solutions. But things become much more interesting in multiple dimensions. So here's an example of a convex polyhedron in 3D. This corresponds to the case where there are three variables, and you can think of a hyperplane that, or a plane in this case, just normal plane, that is situated somehow in the 3D space, and you can move it to find a vertex which corresponds to a maximum or a minimum of the linear programming problem. But of course, linear programming was made to work in very large dimensional spaces, where things become really a lot more complicated. The bottom line being is that every time it's a polyhedron, which is defined in some dimensional space, and we are optimizing a linear function. Now, of course, it could be that the constraints do not leave any access, any plans to be admissible, in which case the problem doesn't have a solution. Okay, let's look at a simple example. This is an optimal production portfolio example. Imagine a company which is producing two goods, A and B, and they have a certain technology which imposes a particular constraint on the production. These are some complementary goods. I don't know, think of oil being converted into different oil products, and there is certain dependence between how much of each of the products that you can make from you know, a unit of crude oil. And you know, let the constraints be given by the system. So the difference between x and y cannot be too large in both directions, and there are some constraints on the total resources, and let this give the profit function. Can we convert this into a linear programming problem? Well, we noticed that the profit function is linear, and all of the constraints are of the form matrix A times x less than or equal to b, and so it does look like a linear programming problem. Well, can we rewrite it as a linear programming problem? Indeed, here's the matrix A that incorporates the constraints. So, for example, this one, minus 1, 1, what does it mean? That's basically minus x plus y must be less or equal than 4. And that corresponds to the to this first equation, and so forth. And the two bottom rows here, they correspond with the corresponding zeros. They incorporate the non-negativity constraints. Here's a picture for the problem. You can see, if you look hard enough, you can see in blue lines all of the constraints that are which I just presented, and the red lines show the direction of the objective function for this problem. And it's easy to see that the solution is given by this point here, where the objective function is maximized. Well, let's try to arrive at the same solution using Python. And here's how we do it. We need to use the leanprog function, which is part of the SciPy package and subpackage optimize. This essentially implements a solution, one of the algorithms to solve the linear programming problem. And so we just need to encode all of the matrices and arrays and vectors that are in the problem. So essentially just these matrices. So C is minus 2 minus 1. We want to maximize, but the solver solves the minimization problem, therefore we put minuses there. A is the matrix as it was written on the previous slide, and then B is also given on the previous slide. Now the solver has this callback function, which we will use to output some intermediate results, the number of iteration, and the current solution, the current x, which is the current x leading to the current maximum of the function. And that's about it. So if I run this code, here we have 3 iterations that the algorithm is doing, and the solution is found nicely, optimization terminated successfully, and the found solution is indeed 6.4, as we would expect from this picture here. Well, obviously this is a trivial example, just to illustrate the work of linear programming problems in Python. But in the next video, we will look at a lot more interesting example that has to do with calculating an optimal reallocation of probability mass. But this short video on linear programming stops now. You can find more information in the book. Alfred Galashon is the researcher, the scholar who is developing the optimal transport problems in the real and modern applications. Here's, by the way, a link to his very recent plenary talk. Let me at the Chemistry Society World Congress, which is just from last week, actually. But this is it for this video. See you in the next one.